In a differential pair, when you have phase and delay tuning, where do you put those little bumps on the differential pair? Do you place them right after the phase mismatch, in between the phase, or long after the phase mismatch? Does it even matter? Well, in this video, I'm going to answer that question. We're also going to cover skew, also phase delay, and why where you adjust that phase delay is extremely important. The principles that I apply here apply to all differential pairs. I just happen to be showing this in an Allegro X PCB layout. By the end of this video, you'll know what constraints to set so that you are routing your differential pairs correctly and they don't fail on you in between 2 to 3 gigahertz. Okay, so for any differential pair, they need to be coupled the entire way, ideally. Where you may get uncoupling of the differential pairs, which can cause noise, EMI, and issues on your differential pairs. Where that can happen is when you need to break out into a BGA chip or just break out in general into routing into copper pads. Let me show you where you can set that. So let's go to Setup, Constraints, in the Electrical Constraints mode. And here we have our differential pair set of constraints. We have multiple columns here, which is what I refer to as my timing toolkit, where they address uncoupled length issues, issues with static phase tolerance, and I'll explain each of the problems these timing constraints are solving. First though, uncoupled length, we want to avoid any noise from uncoupled traces. This max length tells us how long are we allowed to have our two differential signal traces to be separated or uncoupled from each other. How long are we going to allow that to happen on the PCB? Depends on your requirements, your board, your communication protocol, and what have you. But typically, you're going to be seeing 100 mils to 200 mils on a high-speed PCB, typically. All right, I set mine to 150 mils. So let me show you how that is enforced. I go ahead and route on the PCB. We do route connect, and I say, hey, I want to route from these two pads on the PCB, start my routing, and I'll eventually get to my destination. I won't end that. I'll just end it here. Currently, these two traces, they are not coupled coming off the pads of this PCB, but because they are coupled soon enough, like this distance, I would measure from the start of this pad to here is less than 150 mils. Now, if I were to do the same on these two pads, we have a little bit of red, with a little bit of complaint saying, hey, you are outside of the allowed uncoupled length or distance. So I click and place and route that and see I am outside of that allowed 150 mils. Here it's saying, hey, you're at 152 mils, not 150. You need to fix that. All right. This helps us avoid noise issues and EMI. Okay, so another problem that you'll run into when it comes to differential pairs or just high-speed signaling in general is a timing issue. If there's a mismatch in between the signal that travels on, say, differential pair line 1, the signal that goes on this trace, it's pulsing, it's propagating along this signal trace, right? And then it's received at the receiver at a certain time, say T0. Whereas the signal, the opposite signal on the other trace, it's propagating along, right? And it arrives later at time T1 because maybe the length is different on the other trace. If they arrive at a different time, what the differential receiver is going to get is two signals arriving at the wrong time from each other. So instead of looking like they're supposed to look nice and equal and opposite, instead of looking like this, for the differential receiver to take the difference between the two and give you a nice clean positive signal and a nice clean double negative signal. Well, not negative, but 0 or 1. Instead of that, you will get skew, and then your receiver is going to distort that. It's going to get half the value or some of the value at half the time. It's just going to be all messed up. This is where we have skew problems. How do we solve this? Well, we need to make sure the differential pairs are the same length everywhere on the PCB and that they're matched. To enforce this, I'm going to go ahead in my constraint manager, go to Setup and Constraints, Electrical, and in the differential pair, we are going to force a static phase tolerance. We will only tolerate a 20 mil difference in the differential pairs. Okay. Now, really, this should be based on timing So let's say we don't want more than 10 picosecond difference, but we'll do it based on length. So you see both. So we'll go with 20 mils. And what this says is, let me intentionally introduce some delay on a differential pair. I'll use differential pair tuning geometry and I'll set this to say 45 degrees and intentionally introduce some crazy delay here with the traces. The signal has to move along a farther distance on one of the traces, but not on the bottom one. This is our timing mismatch. This is our skew that I showed you earlier. And notice in the lower right, static phase is off by 268.5. That's a problem. So I'm going to drop that in there. And the DRC is warning us to say, hey, you're going to get your constraint value set to 20 mils. You're 288 mils off. So how do we solve this? We are going to introduce just the same amount of delay because we can't speed up the signal. Okay, we have to introduce just the same amount of delay on the other trace to make this work. Then your static phase is going to look at that and say, hey, yep, you're evenly matched. Pretty good. Now, instead of both signals arriving at separate times, they arrive at the same time. Let's go ahead and see what the DRC says. Constraint. So the constraint is fixed for the static phase tolerance, which means we've fixed the skew problem. However, we still have the uncoupled length problem. See what I did here? Because I have these differential pairs uncoupled for longer than a specified distance and just uncoupled entirely between the signal traces, this is a problem. So it's not sufficient to just introduce delay bumps whenever we feel like and wherever. If we want to avoid noise, crosstalk, and the uncoupling of the differential pair fields, then we need to be more careful with how we introduce our delays. But that's just to demonstrate how to fix the skew problem in a differential pair. So let's say I don't want to do the bump thing, which is not good for sure. And we want to route in such a way that we can manage the static phase. We can do it by going a little bit down and a little bit up at these different angles. Now, depending on if you're trying to do fiber weave aware routing, making sure that you're at specific angles to avoid being skewed too much by the fiber weave, take a look at that. The static phase lets us know in real time how far off we're going. And I may need to go up. I may need to go down and bend around to maintain the proper phase between my differential pairs. You see how careful we have to do that? And just pay attention to the arrival time when routing our differential pairs. See, we are okay for static phase. We're out of sync, so that's something we want to fix. Ideally maintain always. A little under there. Okay. Notice the more I stay in a straight path, the more I can maintain my static phase because both signals are not having to traverse different distances, right? Less skew. So here I know there's going to be a little bit of a difference in the skew. I'm going to double click, add vias onto here, drop those via directly onto the pads, and then do a little bit of a slide here to have those overlap. I mean, that's if you allow for via and pad. And notice because I maintained and use certain routing, I maintain that static phase, and now we have no issues. So that's a strategy that you would employ to maintain static phase while moving around different obstacles. However, there's another problem. Well, if your two signals are out of phase long enough, you're going to introduce common mode voltage because of the instantaneous mismatch in phase from one trace to the other. That's right. Because the signal took longer to travel, or it'll take longer to travel along this longer distance, because you see here, this is longer, kind of like a racetrack. And the signal on the bottom has less racetrack to go through because it's traveling at the same speed. There is now a phase mismatch. So I pulled up Paint to demonstrate this issue. You have one signal pulse traveling at a certain speed, right? So that's the pulse. And I'll just draw an arrow to show that it's traveling at one speed. The other signal pulse is traveling at the same speed along this trace, opposite in voltage and whatnot, same speed, and there we go. At this point, we'll call this point A, both signals are arriving at about the same time. However, here, signal B on the bottom propagates down here in the same amount of time, and it's around here this way, this front part of the signal, whereas the signal at the top, the red one, is only around here by the same time. Now there's a mismatch in the timing of the pulses, and this is happening at millions to billions of times per second, depending on the frequency of your protocol. That coupling mismatch in the electromagnetic field is then going to introduce a third field, which introduces a third voltage traveling on its own path. So now you've got three voltages. This is the common mode voltage. It can show up at any time when you have that signal phase mismatch. So just because you have them matching at the end of the receiver in total time to avoid skew, that doesn't mean you won't get phase delay problems and common mode voltage problems due to phase mismatch at anywhere along the PCB. So how do we manage that? Well, we go into the constraint manager, set up constraints electrical, and we have to enforce dynamic phase delay. What's the max length we're going to allow the phases to be out of sync from each other? Some engineers will be extremely strict with this. Typically 10 mils is sufficient. You can even get away with 20 mils depending on the protocol, to be quite frank. So let's set this to 20 mils. As for the tolerance, you don't want to tolerate too much on the dynamic phase delay. Well, let's say go with 5 mils, and there you go. Now it's better to set this in picoseconds, to be quite frank, because dielectric material changes. Dielectric constant changes amongst materials, and your distance is going to change the delay time based on that material. So it's better to set a timing so that regardless of the material or distance or spacing you're working with, it enforces the timing. The field solver in the constraint manager and in the tool is active all the time and always actively solving for these constraints based on the materials, the stack up, everything. So that's why I like to enforce the timing. You'll also see something like 1 picosecond dynamic phase tolerance. Really depends on the engineer and how strict they want to be. So with that being enforced, now we have our rule showing us in our routing plan. Here, yeah, we route it so that we got a good static phase to avoid skew, but now it's revealing that, hey, we are out of phase a little too long on this part of the routing path. You need to adjust that. So now I've got to go in, slide this, okay, and change this up a little bit, tune it up, and adjust these so that I do not run the risk of introducing common mode voltage because the phases were out of sync for too long. That means in general, the straighter you can make a path, the better, and that'll help solve that problem. But in some cases, in fact, in many cases, you can't just slide this around and get the phase tuning that you want. Sometimes obstacles are in the way. Sliding may not be sufficient. So how do we solve this problem? This is where we have to introduce delays in the traces, but at the right time. And I'm not just talking about time delay. Time delay, like the bumps you introduce for time delay, can help you manage the overall lengths to avoid skew problems. And that's what we've done here. Here, I'm talking about phase delay, where we need to manage this phase in real time at every instance among the trace. So let me show you what I'm talking about. So here's the question this brings up. Where do you put the delay and phase tuning on the differential pair? Well, you want to do that right after the phase mismatch starts to happen. You don't want to wait, because the longer you wait, the more common mode voltage, noise, and EMI you're going to have admitted through or emitted through the PCB. You don't want that. So as soon as the phase delay or the phase mismatch happens, you want to drop in that delay tuning bump on the trace. Another reason you want to do that sooner than later is because the longer that phase mismatch is happening, the more you're going to need to compensate for that later on in the signal traces. So 2 reasons: you're going to have more EMI and noise, and also you may need to use more copper bumps, like more phase delay bumps, to compensate for the mismatch in phase. This is really a EMI and noise problem that's disguised as a timing constraint in your software. That's really what's going on here. So in the constraint manager, I went ahead and relaxed that constraint a little bit. If we go into constraint manager, differential pair, the dynamic phase, I set this to 2 picoseconds instead of 1. That gives me a bit more room to play with and is more practical anyway, although you will see designs where they set it to 1 picosecond. With the 2 picoseconds, notice that there's the phase mismatch here, 12.56 mils, coming out of this BGA chip and propagating out. It looks like we have enough of a mismatch in the phase or the routing paths, so the phases get mismatched by a little too much. What I'm going to do is, as soon as possible, introduce a little bump to lengthen this trace and see what happens. So I'm going to go to route, phase tune, and then for my line or arc, I'll go with the standard 10 mils and 10 mils that it has here and see what it does. If I introduce that, nope, that's a problem. When I put the bump right here, where this was traveling a little too fast, a little too quickly ahead of this other trace, and I introduced a little bit of a bump or a little bit of a delay to get that in sync immediately. That eliminates the risk or reduces the risk greatly of common mode voltage being generated, stopping it right in its tracks. If I were to right click and hit oops, let's say I put it down later. See, I put the same bump, but further down along the phase mismatch, but a phase mismatch started right here. If I put the bump later down here, that's not going to fix much of anything. Okay, so I need to put it there as quickly as possible to eliminate that mismatch. That's how you want to do it. So real quick, I want you to see how the Nvidia engineers do this. I have the Nvidia AGX Orin 64GB carrier board. And this is the third layer with a bunch of PCIe differential pair traces. Here they are routing this. It has this kind of odd routing pattern because they're trying to skirt around the fiber weave underneath the traces. If you only route at certain angles straight ahead, then you're at risk of causing stacking effects that change the skew of the signals underneath the trace. But in any case, here I want to zoom into delay. This is some phase tuning that they added in here because when they transition from one layer to the next on the board, there was enough of a phase timing mismatch for them to say, hey, I need to introduce some delay in here to make sure these signals stay in phase before they continue going through the rest of the printed circuit board. So in this video, we covered multiple constraints: uncoupled length, static phase, dynamic phase, the skew between the two traces, and the reason behind length matching bump placement. Static phase helps you control skew and timing. Dynamic phase helps you control common mode voltage and EMI. And bump placement helps tie those two ideas together. When these are set correctly, your differential pair would have lower chance of having any issues with skew. They'll have minimal common mode noise and a much better chance of passing EMI and compliance testing.